Good morning, welcome to new lecture. In this lecture, I will solve several examples using virtual work method. Let's look at the first example. Assume we have one cantilever beam and we have point load here at point B. So free end A, B, C. Length for this beam is equal to L and EI is constant. We want to find deflection at point A. You know this beam will deform and we will have maximum deflection at point A. We want to find that using virtual work method. First step, because we want to find deflection at point A, I will apply unit load at point A. So this is unit load, magnitude is 1 at point A. If we want to find deflection, we will apply unit load at that point. If we want to find rotation, we will apply unit moment. Here we want to find deflection at point A, so I will apply unit load. Now, let's see. This distance from point A to point B, it is lowercase a. So, from B to C will be L minus A. From A to B, if I measure x from A to B, x will vary from 0 to lowercase a. In this range, moment, because of this unit virtual load, will be minus x, because if we cut beam at x distance, this is load 1, I want to find mx, here v. If I take moment respect to the cut point, I will have mx v plus 1 times x is equal to 0. If I take x to other side, it will be negative x. Let's look at to see what is the moment under real load. If I measure x from here, and I show free body diagram, here mx real. If I measure x from here, there is nothing over there, so m real, because of real load, will be 0. Let's look at to this range from B to C. So from B to C. Here I will measure again x from B this time. So x will vary from 0 to maximum L minus A. In this case, if I look at the free body diagram under virtual load, what I have, this is point A, point B, and I measure x from here. So I want to find mvx here. This time, because from here to here, it is lowercase a, m. If I take moment respect to cut point O, this time m v will be equal to negative a plus x. Because if I take moment with respect to this point, mvx plus 1 times distance, it will be 1 times x plus a is equal to 0. If I take this term to other side, it will be negative. Moment because of real load, here, again if I show free body diagram, this is load P, A, X. I want to find MRX here. If I take moment with respect to the cut point, I will find MX is equal negative PX, because if I take moment with respect to here, MRX plus P times X is equal to 0. If I take to another side, it will be negative. Now I want to find delta A. Delta A will be equal to, this is the formula I proved last session, moment because of real load times moment because of virtual load divided by EI times dx. Here, for each range, I will multiply here from A to B, because this one is 0. 0 times x will be 0, plus from B to C, if you multiply, you will have 1 over EA times integration minus A plus X minus Px dx is equal to, if I integrate this one, I can delete this one and continue here. So delta A will be equal to P over EI A x squared over 2 plus x cubed over 3 from 0 to L minus A, because this integration, this part is from B to C, so integration will be from 0 to L minus A. This will be equal to P over EI P over EI A L minus A squared over 2 plus L minus A cube over 3. From here, if I simplify that, delta A will be downward, of course, will be equal to P over 6 EI times L minus A squared times 2L plus A. This is first example. So let's look at the second example. Second example is simply supported beam subjected to uniform distributed load, but this time we want to find a slope in one support. So we have simply supported beam A, B subjected to distributed load the intensity of the load. For example, it is lowercase w pound per feet. The length of this beam is L, and again EI is constant. We want to find theta B, slope at point B after deformation. You know this beam will deform like this, and deformation will be symmetrical. Maximum deflection will be at midspan, but these two theta, because of symmetry, they will be equal. We want to find, for example, theta B. What I should do? First, I will find reaction here. The reaction for simply supported beam subjected to uniform distributed load will be W times L divided by 2. Because entire load downward, it is W times L. Because it is symmetrical, so the contribution of each support will be WL over 2. Then we have the same beam, because we want to find the slope in this beam. Simply supported beam A, B. We want to find slope at point B, so I will apply unit moment. Because I want to find slope at point B, I will apply moment and unit moment, because moment will cause slope here. So if I apply unit moment here, what will be the support reaction? Support reaction, for example, AY. I want to find AY. If I take moment respect to point B is equal to 0, what I have unit moment counterclockwise minus AY times L is equal to 0. From here, AY will be equal to 1 over L. So we know AY is equal to 1 over L. If I write summation of forces in vertical direction, AY plus BY should be equal to 0. Equilibrium equation, summation of forces in vertical direction is equal to 0. From here, By will be negative 1 over L. Negative means this support reaction direction should be downward. It will be 1 over L. Here I measure X from left side, point A. So I can write from A to B, X varies from 0 to L, M, V. If I look at the free body diagram, this is X, support reaction 1 over L, M, V, X. If I take moment with respect to cut point, M, V, X, minus 1 over Lx is equal to 0. So if I take the other side, mv will be x over L. If I find moment in real beam under real load, what I have, again, if we look at the free body diagram, M real at distance x, reaction W L over 2, external load intensity is W. If I take moment with respect to cut point, I have mRx minus W L over 2 times x plus W times x over 2 is equal to 0. I am taking moment with respect to cut point, mRx counterclockwise, positive, minus WL over 2 times X clockwise, so negative, plus the moment this distributed load will create respect to this cut point O, it is counterclockwise, so positive W times X will be entire load or resultant force times, where is the location of the resultant force? In the middle, in the centroid of this distributed load. So times X over 2 is equal to 0. From here we can find M real is equal to W L over 2 times X minus W X squared over 2. I took these terms to other side. So this negative will be positive, positive will be negative. Now let's plug all these in formula. The formula I proved last session. Theta B will be integration M R M V over E I dx. This will be equal to integration from 0 to L 1 over EI times X over L times W L over 2 times X minus W X squared over 2 times dx. This will be our integration. This is equal to, because 1 over EI, it is constant, we can pull out of integration. So here we will have W E I X cube over 6 minus X to the power of 4 over 8 L from 0 to L. This will be equal to W L cube over 24 E I. The end result, it is good you memorize, you know it, because you can use that result. If we have simply supported beam subjected to uniform distributed load, theta A and theta B, they will be equal because of symmetry, because the formation is symmetrical, and the magnitude theta A will be equal to the theta B, that will be equal to W, the intensity of the load, L cube, the span length to the power of 3 over 24 E I. Here, theta B, you should know theta B is counterclockwise. So this will be positive. Theta B, you see rotation is counterclockwise, but theta A, it is clockwise, so it is negative. Magnitude, it is equal, both magnitude is WL cube over 24 EI, but the direction theta B will be counterclockwise, positive, theta A will be clockwise, negative. Let's look at the next example. Next example, it is one frame. The concept is the same, but a little bit more complicated. Let's look at this frame. Okay, we have this frame. Both supports are hinged and it is symmetrical. feet, 8 feet, A, B, C, D, E. This frame is subjected to concentrated load at point C. The magnitude of the load, it is 120 kips. This length is 10 feet. Young modulus for material, it is 30,000 KSI. Moment of inertia for all these sections is 2,500 inch to the power of 4. And cross-sectional area A, it is 20 inch squared. We want to find the slope at left side of point C. So if we apply load at point C, this will deform downward. After deformation, we have slope, something like this. So we want to find this slope here in left side of the C to see what is theta C at left. We want to calculate that one. Here, for integration, I will measure in this direction y from here, again y in this direction from here, x from left to right, here x from right to left. I put one dashed line inside of the frame in order to recognize negative and positive internal moment. If internal moment cause compression in dashed line, I will call that moment negative. If internal moment create tension in dashed line, I will call that moment is positive. Let's look at this frame, because we want to find the slope at left side of the C using virtual work method. It is the slope I will apply unit moment, where at the left side of the C, support C. First step, I should find reactions in this frame under real load and in this frame under virtual load. Let's see what is the, for example, EY here, or what is the EX, what is the AX, what is the AY. I can find these using equilibrium equation. For example, if I take moment respect to point A equal to 0, what I have EY times 16 minus 120 times 8 is equal to 0. From here, AY will be equal to 60 kips. Summation of forces in vertical direction equal to 0. So AY plus EY minus 120 is equal to 0. If I put EY here, AY will be 60 kips again. So EY magnitude is 60 kips, AY is 60 kips. In order to find Ex, I can take moment for right side respect to hint C for right side is equal to 0. I will have Ey times 8 minus Ex times 10 is equal to 0. Ey times 8 minus Ex times 10 is equal to 0. Ey times 8 counterclockwise positive. Ex times 10 respect to point C clockwise negative. Because we know the magnitude of Ey, it is 60, so it will be 60 times 8 minus Ex times 10 is equal to 0. From there, Ex will be 48 kips. So, Ex will be 48 kips. Summation of forces in horizontal direction is equal to 0. So, Ax minus Ex is equal to 0. We know Ex is 48, so Ax will be 48 as well. So I will plug here Ax magnitude 48 kips. Let's look at to this one. Again, point A, B, C, D, E. I want to find Ey, Ex, Ay, Ax. If I take moment respect to point A equal to 0, what I have? Ey times 16 minus 1 is equal to 0. From here, Ey will be, if I take the other side, Ey will be equal to 1 over 16 kips. So I can write Ey is equal to 1 over 16 kips. Summation of force in vertical direction is equal to 0. So Ay plus Ey is equal to 0. There is no force in vertical direction, external force. So this is 1 over 16. Ay will be negative Ey if I take the other side. So this will be, again, magnitude 1 over 16 negative. It means I should show in inverse direction. So I will tend the direction downward. Again, if I take moment for right side of the frame respect to point C, I will have Ey times 8 minus Ex times 10 is equal to 0. If I plug here Ey, I will find Ex is equal to 1 over 20 kips. If I write summation of forces in horizontal direction equal to 0, Ax minus Ex is equal to 0, I will find Ax magnitude, again it is 1 over 20 kips. So I find reactions. Now let's look at to the function, and in each part A, B, B, C, C, D, D, E, I will define different function. Let's I start from A to B. From A to B, see what we have. Y, if I measure from here, Y will be from 0 to 10. If I look at to free body diagram. Here, for real load, I will have 60. This will be 48. This will be Y. This will be M real. For virtual one, again, I can draw the free body diagram. This will be 1/16. This will be 1/20. I will measure Y from here. This will be MV. In both of them, for real, for virtual, I will take moment respect to cut point. So axial force, because here we have axial force, I will show with F. Bending moment I will show with M. So in this free body diagram here, axial force on the real one it is -60, on the virtual one -1/16. For real moment, if I take moment respect to here, the MV will be 48 times Y negative MR will be minus 48 times Y, and MV will be 1/20 times Y negative. Because if I take moment respect to here, it will be MR plus 48 times Y is equal to 0, MV plus 1/20 times Y is equal to 0. If I take the other side, it will be negative. So because I don't have enough space, I will remove those. I will write only function Fv is equal 1/16, Fr is equal -60, Mv is equal -Y/20, and Mr is equal to -48 times Y. This is for AB part. AB part like beam column. We have bending moment inside. If we have only bending moment in one element, we will call beam element. If we have axial force in one element only, we will call that element column. Because here we have axial force and bending moment, we will call AB beam column element. Let's look at from B to C. From B to C, X varies from 0 to 8, because I measure X from here, X varies from 0 to 8. Again, if you look at the axial load, free body diagram, axial load, this will be 48 and 60. So here M real. And if we look at the free body diagram, under virtual load we will have 1/20 axial. This will be 1/16. So this will be MV. Again, axial force under real 48 negative because it is compression. Axial force under virtual, it is -1/20 because compression negative, tension positive. If I take moment respect to the cut point here, the MV, MR, what will be the MR here? If I take moment here, let's see. Free body diagram, I draw it because of space, I draw it wrong. Let's say show entire frame. So this is 48, A, B, this is X, and here I have 60, this is N or F and X, this is V, we don't need the V1, and this is MR. If I take moment respect to cut point, what I have for MR, I will have MR plus 48 times 10 minus 60 times X. So I will have MR counterclockwise plus 48 times 10 minus 60 times X is equal to 0. So if I take the other side, MR will be 480 negative plus 60 X positive. So I write this here. So from B to C, internal axial force will be negative 48 because it is compression, and MR will be negative 480 plus 60x. Same thing here for virtual one. For virtual, this is frame A, B, from here to here, for example, X, 1 over 16, 1 over 20. So what is the MV? First, FV will be negative 1 over 20 because this reaction will produce compression axial force in this part. So it is negative 1 over 20. About MV will be MV plus 1 over 20 times 10 plus 1 over 16 times X is equal to 0. MV counterclockwise, I am taking moment respect to cut point, MV plus 1 over 20 times, from here to here it is 10, again counterclockwise, positive, plus 1 over 16 times X, again counterclockwise, it will be positive. So if I summarize everything here, I will have FV is equal to negative 1 over 20, MV will be minus 1 over 2 minus X over 16. From B to C. Now I should continue the same thing for CD part and E part. From E to D, Y varies from 0 to 10. FV will be negative 116, FR will be negative 60, MV will be minus Y over 20, MR will be negative 48Y. From D to C, here we measure Y in this direction and X in this direction. So X will be between 0 to 8, FV minus 120, FR minus 48, MV negative 1 over 2 plus X over 16, R will be minus 480 plus 60x. Again, free body diagram, I draw it for AB and BC part. For EC and ED will be similar, you will draw yourself. So these will be our functions. Now we should multiply these in each region. Here pay attention, because we have axial force and bending moment. Deformation will have two parts. Deformation for axial, deformation in AB part, BC part, CD part, DE part. Deformation because of the bending moment in AB part, BC part, CD part, ED part. We should add all those together. In real life, if we have in plane structure 2D structure, we have axial force, in general case, we have shear force, we have bending moment. We should consider all three. But because shear force deformation for normal beam, it is smaller. If we compare with bending moment deformation, we neglect that part. But axial force deformation can be large and we cannot neglect. So here we will not neglect. Let's see what will happen. I should remove all these. You can write this down in your note, because I will remove it, but I will use it. I don't have enough space here in order to continue. So I remove all these. Now, because we will consider deformation because of axial force, theta C at left, CL means slope at left side, will be summation of axial force deformation, FV, FR times L over EA. Axial deformation, we will put EA. We know axial deformation, it is internal force times length over EA. Summation of those, plus bending moment deformation, summation for all element, MV, MR, DS over EI. Because some of them it is dy, some of them dx, so I wrote as a formula ds. Now I will plug everything in this formula. I will plug one by one and then I will add together. Let's see if I plug everything here what I will have. I will have 1 over EI, because we have 12 these two from 0 to 10, negative y over 20 minus 48 y dy plus from 0 to 8 minus 1 over 2 minus x over 16 negative 480 plus 60x dx plus from 0 to 8 minus 1 over 2 plus x over 16 times negative 480 plus 60x dx plus 2 over EA negative 1 over 20 minus 48 times 8 plus 1 over EA times 1 over 16 negative 60 times 10 plus 1 over EA minus 1 over 16 minus 60 times 10 is equal to, please write this one by one. I will write the final answer here. You see, we should integrate all these, and here we don't need integration for axial deformation. So, if I integrate and I plug numbers, what I will have? Finally, I will have 1 over E I 1.6 y cube from 0 to 10 plus 2 times 240 minus 15 x squared from 0 to 8 plus 38.4 over EA is equal to, if I plug number here, I will have 3520 EI plus 38.4 EA is equal to. This will be 3520 instead of E 30,000 KSI. If I convert to the feet, 144 I 2,500. If I convert to the feet, 144 times 144 plus 38.4 30,000 KSI times 144, because I wanna convert to the feet from inch. 12 times 12, A 20 divided by 144 is square. So, the final answer, if I write here, the final answer, theta will be equal to 0.06824 radians, and it will be clockwise. Clockwise, usually we show it negative, and it is clear this slope should be clockwise. You see the deformation. If I draw deformation, this roughly will deform like this. Point C will come here, this will bend, this will be almost 90 degrees. Other side exactly the same thing. So slope here will be this theta CL, and you see it is clockwise. Thank you so much for watching this lecture. See you next session. Bye bye.